everybody to the second session of the morning. And first off this morning, we've got Mauricio Sadinle.
Close enough.
Almost, yeah. Who's has interest in record linkage, missing data and classification, which I guess you'll be touching upon in this morning's talk, which is about a Bayesian partitioning approach to duplicate detection and record linkage. Thanks.
Yep. Thank you. Really glad to be here sharing with all the world experts on record linkage. So thanks for the invitation. So first of all, I'm going to present an approach to duplicate detection and record linkage. So I guess the first thing that I should clarify is why do I put both terms there in the title, record linkage and duplicate detection. Well, at least in the statistics literature, traditionally record linkage refers to the task of linking across multiple data files, whereas duplicate detection refers to the task of linking within one data file. And so making that distinction can be important because if we have multiple data files that are collected from in different ways, like administrative data, surveys, those data sources, each of them might be subject to different types of errors, right? They might have different quality. So it's important to keep that in mind. Whereas in record linkage, whereas in duplicate detection, we are usually assuming that we have one data file that was collected under, let's say, the same generating process. So what are the what do the traditional approaches to solve these tasks do? So we have supervised approaches that essentially use classifiers, right? And we have mixture models. And we have heard throughout these days about these two approaches. What they have in common is that they output independent decisions, independent pairwise decisions for pairs of records. So you can, for example, you can declare, or your method might declare that records A and B are linked. It might similarly declare that B and C are linked, but it might also declare that A and C are not linked, right? So this is a transitivity issue here. I mean, the linkage decisions, the matching decisions should be transitive, right? But because we are using those approaches, pairwise decisions, we might have this type of problems. And so what we have to do in practice is to resolve those somehow, right? And as far as I know, there isn't a principal way of doing that. Some people take the transitive closure, but then you are saying that a linkage decision is more important than a non-linkage decision, right? And at the end of the whole process, there is no proper account of the uncertainty in the linkage decisions that you are taking. So what I did for my thesis was to think about those issues, and so I came up with an approach to do joint duplicate detection and record linkage, and it uses a Bayesian framework. So this framework allows us to guarantee that whatever linkage decisions we take are transitive, and the Bayesian approach allows us to incorporate prior information. For example, if you have prior information on the overlap of the files or on the quality of the fields, we can incorporate that information in this framework. And because it's a Bayesian framework, and because of the way it's set up, it provides a proper account of the record linkage decisions. So first, I'm going to tell you about the general skeleton of the framework. So let's think about this example. We have three data files, right? We could think of putting them together under the same sort of format, right? And we could think of concatenating one under the other. So this is let's call this the concatenated data file. If we can find a partition of the set of records in such a way that coreferent records are clustered in the same element of the partition, then we will be solving jointly the duplicate detection within file and the linkage across files, right? So what does that mean? That means that the goal of joint duplicate detection and record linkage is to partition the data file, right, into groups of coreferent records, right? And so what that means really at the end is that the final parameter of interest of the whole process is a partition that I'm going to call a coreference partition. And of course, a partition can be represented in different ways. One way, which is not very efficient, would be using a matrix, right? Whose ijth entry is equal to 1 if records I and j are coreferent and 0 otherwise, right? That would be one way of representing a partition. Another way is by introducing a labeling of the records. So for example, if you have R records in total in your concatenated file, then you can introduce one label for each record. And if you can ensure that two records have the same label if and only if they are coreferent, right? That's another way of representing the coreference partition. So there are different ways of representing it, and I'm going to use one or the other depending on what's more convenient. So here's the general skeleton of the framework. So we have the traditional comparison data, right? We have a vector for each pair of records. Presumably, there's one comparison for each field that the data files have in common. And the model is very similar to a mixture model. Okay, so we're going to have one distribution for matches. Here, delta j means that the pair is a match. So we're going to have one distribution for matches, one distribution for non-matches. So that's pretty much the same as the traditional mixture model, right? What's different here, first of all, is that these distributions are indexed by the pair of files. So what that means is that you're going to give a different treatment to records that come from the same file, or to pairs of records that come depending on which files they come from. So by doing that, you will allow these distributions to adapt to the different types of errors that the files might have. And what's different also is that now these indicators here, these matching indicators, let's say, they are not independent of one another, but they are determined by a structure that represents a partition. And so therefore, since this is a Bayesian approach, we have to put a distribution on partitions on that space. Okay? And at the end, we're going to obtain a posterior distribution on the possible partitions of the data file. And our linkage decisions are going to be based on that posterior distribution. Okay. So this approach can be, so that was the general skeleton, and it can be specialized. It can take particular forms depending on the specific problem. So for example, if you just have one file that was collected homogeneously, then it's a typical duplicate detection problem. So that's a piece that is out there already in the Annals of Applied Statistics. Now, if you have the traditional record linkage scenario, if you have two files and no duplicates, then it specializes in certain ways. It allows you you can take advantage of that structure to derive more things, and I'll give you some details. So that's a piece that is about to appear in JASA. You can also use this framework to account for the linkage uncertainty, to propagate it into subsequent models. For example, you can use it for population size estimation using some of the models that Patrick mentioned before, decomposable graphical models for population size estimation. So my original plan was to emphasize this part in this talk. But then based on what people have presented here so far, I decided it made more sense to emphasize the second part. So if anyone is interested, I would be happy to talk about the third part also. You can ask me about it later, but then I'm going to give you the details of the second part. Okay. So what is the traditional record linkage scenario? We have two files, right? And we assume that they don't have duplicates. Okay, and we want to identify which records refer to the same people. But because we assume, because we have only two files, and we assume that we don't have duplicates, that imposes a specific structure that we have to guarantee. And there might be a lot of uncertainty. For example, here's a toy example where this John Doe appears here with multiple dates of birth. They could be different John Does. We don't know. This person here doesn't have middle initial, doesn't have date, and I'm sorry, it doesn't have day and month of birth. So who knows who is the right match? So how has that problem been solved? The famous Felix-Hunter approach for record linkage was designed for this scenario. So you have seen so far, I think, this formula a couple of times this week here. So Felix and Hunter derived a decision rule, and they claimed that it was optimal under certain conditions, right? They claimed that it was optimal in some sense. However, I argue that the optimality of this decision rule doesn't happen in the context of record linkage, because when you look at this decision rule, the comparison vector alone determines the linkage decision. The problem in record linkage is that we know that the linkage decisions are interdependent of one another, right? So if you just use Felix-Hunter, I mean, you think that you are using an optimal rule, but actually it isn't in at least in the context of record linkage. This decision rule was derived, essentially it's an application of Neiman-Pearson hypothesis testing, and in that context it is fine, but not here. Now, the way that it's usually implemented is using a mixture model, right? So it's similar to what I presented so far. So you have two models for matches and non-matches, right? But what makes it a mixture model is that the matching statuses of the pairs are essentially IID from a Bernoulli distribution. So they are independent of one another, right? So this is like the most, I would say, one of the most popular implementations. There are ad hoc approaches of implementations of Felix-Hunter, but I think this is the most principled one. The problem with this approach is that the mixture components may not always be associated with matches and non-matches, right? So in particular, think of an extreme example where you are linking two files that actually don't have any overlap, right? If you run this approach, it is still going to give you two clusters. But the two clusters are not associated with links and non-links. And this problem is widely known. Bill Winkler has documented the problems of this approach. Right. So, but even if the mixture model is successful at identifying the two clusters, and if you use just the Felix-Hunter decision rule, you may end up having this kind of chains of decisions that you have to resolve in some way, right? So that's an issue. So what went wrong in the whole thing? The whole problem is that we are treating the matching statuses as independent of one another, right? And they are not. So what is the actual target for record linkage? In the bipartite case without duplicates within files. The actual target corresponds to a bipartite matching. And this term bipartite matching it just comes from graph theory. And what it means is that we have two sets of nodes or objects that are joined by edges, right? And what makes it a bipartite matching is that there are no edges connecting elements of the same group or of the same set. And each node or each object participates in maximum one edge, right? So that's what makes it a bipartite matching. And it's easy to see that for bipartite record linkage, for the scenario that I'm talking about, that's the structure that we should be searching for, okay? So now, of course, there are different ways of representing that, and the way that I'm using is using a labeling of the records in the smallest file. Without loss of generality, I call it x2. So there's going to be one label zj for each for the jth record in the file 2, and that label is going to be equal to I if records I and j are coreferent, and it's going to be equal to n1 plus j, where n1 is the size of the first file, if record j doesn't have any match in the first file, okay? And of course we ensure that the labels are different for all the records in the second file. So for example, here z1, right, the label for this first record is going to be equal to 1 because it matches to 1. The label for the third record is going to be 8 because it doesn't have a match, so it's 5 plus 3. So it's very simple way of representing the bipartite matching. So now if we go back to Fehler-Gisanter, to the Fehler-Gisanter approach. So how do they ensure the one-to-one matching? So Jarrow, in this paper, essentially proposed to take the weights that come from the Fehler-Gisanter weights, let's call them like that, and plug them into a linear sum assignment problem, right? So that's sort of a post-processing step that they do, and then with those weights, then you can ensure that you have you can ensure that you satisfy the maximum one-to-one assignment. But then, of course, this is a post-processing step. This wasn't enforced in the estimation step, okay? So what is the approach? So how does the general approach that I presented at the beginning specialize for this case? So it's very similar to the mixture model approach. So now we also have a model for matches, for non-matches, right? But now the matching statuses are determined by a labeling of bipartite matchings, and we put a prior distribution on bipartite matchings. Okay, so what is the distribution that I'm using? It turns out that I came up with a prior that actually was being proposed by Mike Larsen, who's also well known in this world of record linkage, or at least in the world of Bayesian record linkage. And so the way that you build the prior is that you take the overlap of the files as being distributed according to a beta binomial distribution, and this alpha and beta here can be used to incorporate prior information on the true overlap of the files. And now given the overlap of the files, all bipartite matchings with the same overlap are equally likely. So that's what I call the beta prior on bipartite matchings. So now you can, I mean, that was kind of a general structure there. So you have to put a specific model for the comparison data, right? So what I did was very simple, the simplest thing that you could do. Well, maybe not the simplest thing, but I assume that the comparisons are independent. So that's the traditional conditional independence assumption, right? So here's something similar with yesterday's talk with Harvey Goldstein, and is that to build the comparison data for each field, I compute levels of disagreement. So that's a very natural idea. Actually, I took it from a paper of Bill Winkler, from Bill Winkler as well. So now you don't have binary comparisons, you have some categorical variables, so just model it according to a multinomial, and you put standard flat priors on that, on the parameters of the multinomials. The estimation is done using MCMC, so I'm not going to bore you with those details, because we don't have enough time. But what I actually want to tell you more about is based on a posterior distribution on the space of bipartite matchings, we need to derive a point estimator, right? Because at the end we want to know you could use the posterior distribution depending on what's your goal, but if you simply just want to match, you want to take a point decision, record A links to record B, right? You need to derive a point estimator, right, from the posterior distribution on the possible bipartite matchings. So the way I propose to do that is using this loss function. This loss function essentially adds the loss that you would get from making mistakes linking each record in the second file. So it sums over the losses over all the records in the second file. And the individual losses are given as follows. So if your estimator makes the right decision, then your loss is 0, right? I also allow the estimator to say sometimes, I don't know, right? For those cases that are very uncertain, it's depending on the application, it can be desirable to allow the estimator to say, I don't know, for some cases. So that's why it's called in classification, that's called a reject option. So of course a rejection has certain loss. There's going to be another loss for false non-matches. There's going to be another loss for what I call false match of type 1. That happens when actually the record in the second file doesn't match any record in the first file, but your estimator says that it matches some record in the first file. So that's one type of false match. Now the type 2 false match is when your estimator says that it has a match, and indeed it has a match, but it's not the same match so the true match is not the same that your estimator is saying. So actually that's more problematic than the other type of false match. So you can specify these losses here, and actually you don't have to specify them like in absolute terms. You can only, for example, you can say simply a false match of type 2 is twice as bad as a false match of type 1. That could be, you don't have to specify like in absolute terms. So for the generic applications that I have considered, taking a false match of type 2 being twice as bad as the other possible mistakes, it seemed to have a good performance. So I guess this could be a good, just like a generic implementation of the method. But you can derive point estimators regardless of the value of the losses that you put there. And if you don't want to specify, if you don't want to allow the estimator to say I don't know, then this loss is essentially set to infinity. So your estimator will never make that kind of decision. Okay, so in general, you can derive the point estimator using an assignment problem. So it's an optimization problem in general. But for a wide range of values of those losses, it turns out that the estimator has closed form, and you can obtain it from this formula, which I'm not going to go through. But that's nice because, you know, having a closed form solution, if you have many records, that makes your life easier. So now I run a very small scale performance comparison. So what I did was to consider different scenarios of files overlap and measurement error that I'll tell you about. For each of those scenarios, I used 100 pairs of synthetic data files. And each data file has 500 records, so it's very small scale, nothing like what you guys have worked on. And each file has 4 fields. So it's a challenging scenario because we don't have a lot of, information to match on. And I use the code generated by Peter Kristen and Dinusha, right? So yeah, thanks for sharing that code. So what do we have here? We have two rows, right? The first row corresponds to the results on the under Felix-Hunter. What I did was to fit a mixture model using the same conditional independence type of model, similar to the one that I'm using for my method. I ran it through the Jarrow approach to ensure one-to-one links, and then I also in this case that's the whole thing. That's all I did, and well and the second row corresponds to the method that I proposed. Now there are a bunch of lines that you see there. The solid lines correspond to the precision of the method, and the dashed lines correspond to the recall of the method. Okay, and you can see, I mean, there are black lines and gray lines. So the black lines are the median performance, and the gray lines are the first and 99th percentiles. And so the first column corresponds to files with 100% overlap, 50% overlap, 10% overlap, and the fields could have 1, 2, or 3 records. Okay. Okay. So what can we see here? We can see that if the files actually have a high overlap, then the Felix-Hunter approach works really nicely, right? So look, the recall and the precision are really high. Okay, and the same thing happens for the approach that I'm proposing. The problem with the Felix-Hunter approach is that as soon as the overlap decreases, the performance decays. So the precision, you can see here that the precision is going down. So what that means is that the Felix-Hunter method is linking more than what it should. Okay, and the reason is that you can imagine that if the files have a small overlap, it's going to be very difficult for the mixture model to capture that tiny cluster of matches compared to the vast majority of pairs that are non-matches. That's why it's so difficult in that case. You can see that the method that I'm proposing, the performance doesn't stay perfect, but it doesn't suffer as much. Okay. So I think that's very promising. Now, I wanted to also run a comparison between the two approaches using the two possibilities of allowing for the method to say I don't know for a rejection, right? Of course, the two approaches are not exactly comparable, but these plots here, I think the most interesting thing is that when you use the Felix-Hunter decision rule, you end up having a lot of pairs without decision. So that means that you would be, for example, sending a lot of pairs to clerical review, right? And even doing that doesn't improve very much the performance of the method. And my method doesn't seem as bad in that sense. So now, what is the take-home message? So if you're going to remember 3 things of this talk, I want them to be the following 3 things. First, the optimality of the Felix-Hunter decision rule is not really, you don't meet the requirements in practice, at least in the practice of record linkage. The mixture model can fail really badly, especially if you have a small overlap of the files. And this new methodology seems to be promising and performs much better. So at least keep those 3 things in mind. So that's all. Here's the reference for the paper if you are interested. Thank you.
Thanks very much, Chris. Unfortunately, with time, we've just got time for one quick question. Yeah.
You had results about linkage quality, but nothing about the runtime of the 2 methods. How does it scale with the number of records?
Okay, so the runtime for these simulations was about 40 seconds. So you have to keep in mind that you're running an MCMC. So depending on how long you want to run it, for this it was 40 seconds for 1,000 runs. And 1,000 runs includes passing through the whole records in the second file. So, yeah. And for another application that I have from some data from El Salvador, I have two files, one with 4,000 records and one with 2,000 records. And it takes about 20 minutes to run 1,000 iterations. So I mean, I'm not saying that this is going to solve all the record linkage problems in the world, because it's really difficult to use it for very large data files. But if you can bring it down to small clusters, you can do it. Yeah. Thank you.
Thanks very much.
Oh, yeah.